This is one of the preliminaries lecture series. Now in mathematics, the idea of a set of points that are within a certain distance to a single fixed point is fundamental. In three-dimensional space, this fundamental idea takes the form of a ball. In this lecture, we shall study balls in one-dimensional space, and we give them the name intervals. Okay, intervals. Intervals are special subsets of the real line where these sets are fixed by two numbers. Yes. So, for example, let's take the set of all real numbers where the numbers are between 2 and 5. You see, the numbers 2 and 5 fix this set. You see, so that is why we write them as 2 open brackets 5. You see, the open bracket simply means that, and these are what are called endpoints, and this is the left endpoint and the right endpoint. Okay, or they're even called boundary points because as we see, they will be the boundary of the set. So if I draw them on the real line, you see, these are numbers that are to the right of 2 and to the left of 5, but excluding them. Okay, so it's it is this. This is one way to represent them. Another way to represent this open interval. So we call this an open interval because the endpoints are not included. Okay, so this is 2, 5, and another way to actually do them is to represent them like this. So these are two ways in which you can graphically represent the open interval. Okay, right. So now let's say that we do include the points. Okay, so for example, let's say I include if I include 2, this is what is called the left closed interval, and you see I put a solid brackets 2, 5 to show that we've included 2. Okay, other notation can also be like angle. You see, these are also other notation used in other textbooks. If I include both of them, so this is what is called half closed. Another example of a half closed interval is this one, where I only have the right endpoint. So that is just a set of all real numbers which are strictly bigger than 2 but less than or equal to 5. So x can be equal to 5. Okay, and then we also have what is called this is what is called a closed interval, and this is when I include both endpoints. Okay, and because both are included, I just write it as 2, 5. And if these are real numbers like in 2 and 5, this is also given a famous name, and this is what are called compact intervals. This is when you include both of them. Okay, right. So these are okay. So you see, intervals are just specified by two numbers, in the sense that we just pick all the numbers ranging between these two given numbers. Right. Now, another way that we can look at intervals is to consider them as one-dimensional balls. Okay, so they are one-dimensional balls. And what do I mean by that? Okay, so when we think about balls, we think about a central point and points that are within a fixed distance from that central point. Okay, So in this particular case, what I do here is that, so let's consider the interval, let's consider the interval minus 1, 1, okay? So if I draw it on the number line, okay, then it's minus 1 and 1. And so therefore this consists of all the points between 1 and minus 1. So notice that you can regard this as a ball, because a one-dimensional ball, because the center point is actually 0 and the radius is 1. So all the numbers are within radius 1 of this ball. So therefore I write this as B0. You see, 0 is, this is for the center of the ball, and then the radius is actually equal to 1. So this is the radius, right? So this is so this ball can also be seen as the interval minus 1 and 1, okay? Now, so in general, if I have an open interval AB, so remember that it's very good to visualize everything. So if I have AB, notice that this I can always write as a ball, okay? The center is going to be halfway between AB. Now, halfway between AB is easy to compute. It's just, you just take the average of A plus B over 2. So this real number will give me the center of the ball, slap bang in the center, okay? And then the radius is obviously going to be half of the diameter. So the radius is going to be, so the distance is going to be B minus A, and that's the full diameter of the ball, and I halve it to get my radius. So therefore, an open interval AB, I can write this as a ball centered at A plus B upon 2 with radius B minus A upon 2, okay? So, right. So what we're going to now see here is that when we solve inequalities, the solution sets turn out to be one-dimensional balls all the time. Okay, so let's do some examples. So let us say that this is our second example. Let us solve all those real numbers such that 2x minus 1 dominates x plus 3. Okay, so in order to solve this, what I then do here is that I will just do the same as I solve equations. So inequalities go much the same way as equations. I will put letters with letters and numbers with numbers. So therefore I get x is bigger than 4. Okay. So if I put it in slow motion, I minus x on both sides. Notice that minus x on both sides preserves the order. So we have to be a bit careful when we do it. Okay, so this is the intuition, but you see, so remember that sometimes this guy can actually flip. Okay, so when we, although solving inequalities go much the same as solving equalities, we have to go a bit slower. Okay, so let's see whether we really get x bigger than 4. Okay, so we subtract x on both sides so that we can get the numbers. So I then end up with x minus 1 bigger than 3. And notice that this is by order preservation, by translation. So I'm adding the same amount, so the order is preserved. Then I also now add plus 1 on both sides. So I then surely get x is bigger than 4. Okay, so my equation approach gave me the same thing. So notice that in this case, I consider all the numbers starting from 4 all the way up to infinity. So in this case, my solution is going to consist of all numbers starting from 4 but not including 4 and going all the way till infinity. So this is what we call the interval for infinity, right? All numbers 4 and above, right? Let's now do another inequality. Okay, so this is example 3. We have to now solve an equality. So let's solve 2 over x minus 1 dominates 5. Okay. So in this case, so in this case, what happens here is that, you see, we have to be really, really careful now. Okay, so what I then do here is that I will, like an equation, I will actually put everything to one side, so it's bigger than yeah. So I make I like a quadratic equation. I just equate to 0. But yeah, so I just minus 5 on both sides, and I know that everything is preserved. Then when I simplify this, now I simplify it into a fraction. So it's 2x minus 1, 2 minus 5 times x minus 1. Okay. And then I can rewrite the left-hand side as x minus 1. And this is going to be minus 5x plus 5 plus 2, so plus 7. Okay. So it is minus 5x plus 7. Okay. Now, so notice that this inequality is a lot harder to solve than if it were an equation. I mean, if it were an equation, it would be very easy. In other words, if it was minus 5x plus 7 over x minus 1 is equal to 0, then I can just easily just make the numerator 0 and I'm finished. But in this case, what happens here is that we have to make use of the sign table. Why? Because, you see, this is a positive number. So this is a positive fraction. So the numerator and your denominator, it has to be considered simultaneously, you see. So we know that a fraction is going to be positive provided that either both the tops are bottom, both the top and the numerator and the denominator are both positive, or the numerator and the denominator are both negative. Okay. This therefore leads to two distinct cases. Okay. So case 1 is when both the numerator minus 5x plus 7 is positive and the denominator is in fact positive. Okay, so okay, now let's be very careful with how we handle this. Okay, so we proceed much as we solve minus 5x plus 7 is positive, so we proceed as we do with equations. Okay, so what I'm going to do is I'm going to add minus 7 on both sides so that I can get just the numbers and letters separated. So I get minus 5x is bigger than minus 7. Okay, now look at this. We have to be very, very careful because we have to multiply by a negative number to get 1x in the form of, I have to multiply this by minus 1/5 and minus 1/5. But when you multiply by a negative number, remember the order flips. So therefore I get x must be smaller than negative 1/5 times 7 will give me positive 7/5. Okay. This one is, all I have to do here is just add 1 on both sides, and remember adding a translation preserves order, so therefore I get x is actually bigger than 1. Now remember that both the numerator and the denominator have to simultaneously be positive, so therefore we require x to be simultaneously bigger than 1 and simultaneously smaller than 7/5. So therefore this is one solution. Okay. Right, and okay, and then now we then look at case number 2. Okay, case number 2 is when both the numerator is negative and the denominator is in fact negative. Okay, so once again we proceed with k. Minus 5x is less than minus 7, and I multiply out by negative 1/5, so it's going to be reverse the order to get bigger than 7/5, and x is smaller than 1. So because both the numerator and the denominator will simultaneously be negative, this means that x might simultaneously be smaller than 1 and bigger than 7/5. Now this doesn't make sense because there's no number that will lie to the left of 1 and to the right of 7/5, because there's no number that can satisfy this. So this case 2 gives me an empty solution. So therefore, for the inequality to hold, I therefore need my x, you see, to lie between, you see, it's an open interval. You see, it has to lie between 1 and 7/5. So it has to lie between 1 and what? 7 over 5, okay? So it's going to be something like this. That's it, yeah. So you see it's an open interval, or I can write it out as 1, 7 upon 5, and I can then take it like as this open interval in this particular format. Okay, so there's the answer. Now, to expedite this, there is actually a much faster way, and this is what is called using the sign table. Okay, so what we then do here is that we shall simultaneously consider the numerator and the denominator, but we don't have to. There's a quick way to do this rather than going through the a quicker way than going through this. Okay, so the first thing you have to then do here is that when you look at minus 5x, okay, so the first thing here is that we first get the zeros. Okay, so minus 5x, remember it is minus 5x plus 7, that's your numerator, and the denominator is x minus 1. Okay, so what we then do here is that we find out when are they actually equal to 0. So we get x is when x is precisely 7 upon 5 and when x is equal to 1. Okay, so what I then do is I just make my table. Okay, x. So this is okay, so this is to the left of okay, it seems okay. Let me get my whiteboard again. Okay, so okay, it's just jumping about. Okay, so in this case, I get, so what I then do here is that I make 4 columns. Okay, this column is for all numbers to the left of 1, and then this is to the right of 1, and then this is for the case where it is exactly, when x is exactly 7 upon 5 and to the right of 7 upon 5. Okay, so this therefore considers all the cases. Okay, then what I then do here is that then I now consider 7 minus 5x, or minus 5x plus 7, and x minus 1. See, now I consider the numerator and the denominator simultaneously. Okay, so in this particular case, what now happens now is that what happens now here is that I use what is called a test point. So I pick a number that is smaller than 1 to the left of 1, like 0, and I substitute into here. So get 0 plus 7. Okay, so this is so remember this is minus 5 minus this, so remember that this is minus 5x plus 7. So when I make x equals 0, it means that this thing will be plus 7, so he will be positive through the whole region. At x equals 1, I substitute x equals 1 here, I get minus 5 plus 2, so I get 7 minus 5, so that is 2, so therefore he's going to be positive. Okay, so in much the same way, I take a number in between 1 and 7 upon 5. So in this case, I can take the number 1.1, okay, and then I can plug it into here, I get minus 5.5 plus 1, and then so therefore he's going plus 7, so therefore he's still going to be positive. At 7 upon 5, it turns out to be 0, and here I take a number bigger than, so I can take a number to the, or larger than 7 upon 5, like 2. And in this case, I get minus 10 plus 7, so it's going to be negative, yeah, because negative 3, so the negative 3 indicates consistency. Okay, so we do the same case. I take a number that is to the left of 0, an easy number like 0, plug it in, I get negative 1, so it means he'll be negative. At 1, I know he's going to be 0. I take a number somewhere in between 1 and 7 upon 5, like 1.1, and notice that he becomes positive. And then at 7 upon 5 is exactly equal to 7 upon 5, he becomes positive. And then to the right of 7 upon 5, like x equals 2, 2 minus 1 becomes 1, so 1 is positive, so it is positive on this area. So then I then consider my fraction, minus 5x plus 7 over x minus 1. Okay, so obviously plus minus, you will give me minus. The denominator is 0, so it's undefined. Both are positive, so it's positive. Here is going to be 0, and so here is going to be exactly naught, and here it's going to be minus, okay, because minus plus. So the only time when so the only time when it is positive is when, you see, it happens exactly here. You see, exactly here. So notice that the positive, so your fraction is positive when x lies strictly between 1 and what? 7 upon 5. You see? So this is a much quicker way using the sign table. Okay, so this is how we use the sign table.